In today's lesson, we are going to be dealing with the power rules or the exponent rules that we've dealt with in previous lessons. However, now we're going to incorporate negative exponents. Again, we talked about negative exponents in a previous lesson, so if you do need a little bit of a review on that, please make sure you check out that lesson. So just as a warm-up, let's simplify and evaluate the following expressions. So basically, we want to simplify it to a single power and then evaluate it to an actual value. So in the first one, we have 2 to the power of 3 times 2 to the power of 2. So remembering these exponent rules, when I multiply two powers with the same base, so the large number is the same, I have to add my exponents. So this becomes 2 to the power of 5. And then now I can evaluate it. So I can do 2 to the power of 5 on my calculator and get 32. So 2 to the power of 5 is the simplified version. And then the evaluated is the actual number. Again, you may just be able to type in on your calculator 2 to the power of 3 times 2 to the power of 2 and get an answer of 32, but it is helpful in terms of simplifying the expression if we know our power rules and can get it to a single power first. In B, we have 3 to the power of 7 over or divided by 3 to the power of 5. So we have the same base, or the large number is the same again. So that means when we divide our powers, we subtract the exponents. So this becomes 3 to the power of 2, which is our simplified, and then we can evaluate that. 3 to the power of 2, or 3 times 3, is 9. For C, 10 to the power of 3, all to the power of 4. So here we only have one base of 10, but we have a power to a power, because we have this power here, and then it's set to another power of 4. So the rule of this is that I multiply my exponents. So this becomes 10 to the power of 12. So this basically means it's 10 and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sorry, no, there should be just 12 zeros in total. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes. So evaluated is this long number over here, which I can't think of what that actual number would be. But I believe it is larger than a billion. So it might be a trillion, or maybe one further than a trillion. Anyways, that's the evaluated form. For D, 4 to the power of negative 2. So we did talk about negative exponents in a previous lesson. So when we have negative exponents, we can flip it. In this case, it's a whole number or a whole exponent or power. So a whole number over 1. So we flip it, it becomes 1 over 4 to the power of positive 2. What we can do now is simplify the bottom, because I can do 4 to the power of 2. So 4 to the power of 2, 4 times 4 is 16. So the simplified version is 1 over 16. Or the evaluated version, sorry. You could turn this into a decimal if you wanted to as well. But sometimes, depending on the values, the decimals tend to be a little messy or long. So sometimes the fractions are easier and neater. Just as a recap of the exponent rules, which we have covered in a previous lesson as well, so not just the negative exponents, we've dealt with these rules before, and we kind of just use them in our warm-up. B to the power of x times b to the power of y. When we multiply, we add our exponents, so it becomes b to the power of x plus y. When we divide powers with the same base, we subtract our exponents. We also talked about when we have a power to a power, we multiply our exponents, so b to the power of xy or x times y. We didn't use this in the warm-up, but anything to the power of 0 is always going to equal 1. So we talked a bit about that before. Anything to the power of 0 is always going to equal 1. And again, b cannot be 0 in this case, because 0 times 0 or 0 times anything is always going to be 0. So that's the only number or term that doesn't really work in this scenario. And finally, when dealing with negative exponents, generally speaking, we want them positive. So to make a positive exponent, it becomes b to the 1 over b to the power of positive n. You could also think, not really done here, if you do come across a scenario where you have 1 over b to the power of n, or 1 over a positive fraction, that just becomes b to the power of negative n, so just kind of reversed. Or if you have 1 over b to the power of negative n, so you have a negative exponent on the bottom of a fraction, you can just flip that to the top and that becomes positive. So it's highly unlikely that you're going to see these two second ones in some of our lessons or practice questions, but if you do, should be able to use kind of this general rule that we've already talked about to work back to a positive exponent or work back to something else. Now, even though we may have negative exponents, so negative values or negative integers, our power rules still work the same, right? So that's why it's helpful to be able to multiply and add and subtract both positive and negative integers, because when dealing with these power laws or exponent rules, we may have negative exponents. So let's try to work through some of these and simplify them. So we're going to simplify them as a single power and then evaluate. And we want to stay away from just typing this into a calculator. So we want to evaluate it as a fraction or as a whole number if necessary. So for A, 2 to the power of negative 3 times 2 to the power of 5. So here we're multiplying two powers. This means I add my exponents. So negative 3 plus 5. This becomes 2 to the power of 2. And if I want to evaluate it, 2 to the power of 2, or 2 times 2, is 4. For B, 3 to the power of 7 times 3 to the power of negative 4. Again, I'm multiplying exponents or powers together, so power times another power. I'm going to add my exponents, so 7 plus negative 4, or 7 minus 4, becomes 3 to the power of 3, which works out to 27. Now, you don't need to show this step here. You don't need to show the actual calculation to get your new exponent, because again, it is a straightforward, simple calculation. If you like to show it just to stay organized, you're more than welcome to, but it's okay to jump right to this second line, same as if in the first one. For C, 4 to the power of negative 2 to the power of 3. So here we have a power to a power, so that means we have to multiply our exponents. So in this case, it's going to be 4 to the power of negative 2 times 3, which is 4 to the power of negative 6. So now we have a negative exponent, so let's turn it into a positive one. In this case, I would flip it or make it 1 over 4 to the power of 6. And then to evaluate that, I can determine what 4 to the power of 6 is. So it'll be 1 over 4,096 in its evaluated form. And again, if you did that on a calculator, you would probably get a long decimal, which again is fine, but this is a lot neater and we don't have to worry about any rounding errors. For D, 7 to the power of 3 divided by 7 to the power of 5. subtract your exponents when you divide. So 3 minus 5, the top exponent minus the bottom one. So even though the bottom one's larger, it's the top minus the bottom. This becomes 7 to the power of negative 2. Before we evaluate, let's turn it into a positive exponent. So 1 over 7 to the power of 2. And this becomes 1 over 49. For e, power to a power, we've dealt with this already. We need to multiply our exponents. So negative 1 times 4. This becomes 3 to the power of negative 4. With the negative exponent, let's make it positive. 1 over 3 to the power of 4. And now I can evaluate it because I can calculate 3 to the power of 4. And it becomes 1 over 81. Finally, for f, even though I have 3 exponents or 3 powers all multiplied by each other, I can still apply my rule even though, again, I have a positive, a negative, and a positive. So again, when I multiply powers, a power times a power, I need to add my exponents. So this becomes 2 to the power of 2 plus negative 3, or minus 3 basically, and then plus 4. So this becomes 2 to the power of 3, because 2 minus 3 is negative 1, plus 4 is 3, and then I can simplify this as 8, because 2 to the power of 3 is 8. In example 2, or question 2, I'm going to do the same thing, except instead of using numbers, I'm going to use variables or letters as the base. The same rules still apply, we just can't evaluate it. But we do want to express our answer using positive exponents only. So if we have to flip something, then we may have to do that in order to get positive exponents. And that should be a general rule of thumb. You want to have positive exponents only, generally speaking. So that should be kind of your goal anytime you're doing these types of questions. X to the power of 4 times x to the power of negative 7. Multiplying powers, so this becomes x to the power of 4 minus 7. Becomes x to the power of negative 3. Because of that negative exponent, I want to make it positive. So I flip it or put it underneath 1. This becomes 1 over x to the power of positive 3. In B, n divided by n to the power of 6. Again, we've talked about when we don't see an exponent, we can assume that it's an exponent of 1. So in this case, it's n to the power of 1 divided by n to the power of 6. Division, which means I subtract my exponents. Top one minus the bottom one, 1 minus 6, becomes n to the power of negative 5. And again, like we saw in the last example, to make it positive, I make it 1 over n to the power of 5. Now it's a positive exponent. For C, another division. Again, q to the power of 5 divided by q to the power of 1. Again, that invisible exponent is 1. This now becomes q to the power of 5 minus 1 because I'm dividing. So this becomes q to the power of 4. And that's a positive exponent, so I don't need to do anything else. For D, power to a power. So r to the power of negative 4 to the power of 3. So here I need to multiply my exponents. So negative r to the power of negative 4 times 3 gives me r to the power of negative 12, which I can simplify to 1 over r to the power of 12. E, again, I have multiple steps here. I have to simplify the top part of my fraction before I divide. So in this case, w to the power of 7 times w to the power of 2 becomes w to the power of 7 plus 2 divided by w to the power of 11. This becomes w to the power of 9 divided by w to the power of 11. I'm going to bring it up to the side here. I get w to the power of 9 minus 11. Because of division, I subtract top exponent minus the bottom exponent, which simplifies to w to the power of negative 2. And then finally, I need to turn that into a positive exponent, so 1 over w squared. Finally, for f, again, I have a power to a power on the top, then divided by a power to the power on the bottom. I want to simplify these two first, the top and the bottom separately, before I do my division. So looking at the top, z to the power of 4 to the power of 3 means I need to multiply 4 times 3 divided by z to the power of 3 to the power of 6. So I need to do 3 times 6 on the bottom. This becomes z to the power of 12 divided by z to the power of 18. Now that it's division with a single power on top, a single power on the bottom, I don't need to simplify anything else on either end. I can just deal with these two. I'm going to subtract my two exponents. So the top one, 12 minus 18, which becomes z to the power of negative 6. Because I have a negative exponent and I want to express it as a positive one, I'm going to flip it and put it over 1, or under 1, sorry. Oops. So 1 over z to the power of positive 6. So that would be my simplified version as a positive exponent. So the only difference in these examples that we've looked at is we've dealt with some negative numbers here or got negative answers, and we've learned that we can convert those negative exponents into positive ones by using the rule that we've looked at in previous lessons and that we recovered today. If you need further explanation on the actual exponent rules or the negative exponents, please make sure you're looking back at the previous lessons just to review those concepts.